Now comes another application of the use of torques. And that has to do with simple harmonic oscillations. We were able to calculate the period of oscillations of a pendulum. That was relatively easy. Most of you have even learned how to do that in high school. A string, no mass, an object at the end, and you give it a kick and it goes simple harmonic if the angle is not too large. But now suppose you have a ruler like this, and you have here a little pinhole, and you're going to oscillate it like this. What now is the period of oscillation? That looks like a mathematical headache. And yet, with the knowledge that we have now, this can be solved quite easily. And we can make a quite accurate prediction about the period of oscillation of this rather complex system. Even a system as bizarre as this hula hoop, which oscillates about that pin, can now be calculated very easily with the knowledge that we have, or at least that you will have very shortly if you spend the time and you study this. So let's first do we first take the ruler. This is a ruler. The ruler has mass m and length L. This is the center of mass of the ruler. And I force it to rotate about point P, put a pin through there, nearly frictionless, and the separation between the center of mass and P, I call that now B, as in bridge. This angle is theta. It rotates about the pin perpendicular to the blackboard. For sure, there will be forces through that point P. I don't care about that, because now I'm not going to negotiate with you about which point I'm going to take the torque. I will insist on taking torques exclusively through that point P, so that I get rid of any forces that go through that pin. Any forces that the pin exerts on the object. Gone. Don't care about it. All I worry about now is this mg and this position vector rp. That determines the torque. And the magnitude of that torque, and I'm sure that torque is going to change in time, equals mg times this distance b, but I have to take the sine of this angle theta, because remember, it is a cross product between r and f. And the cross product has the sine of the angle in it. So the magnitude of that is going to be mg times b times the sine of theta. This is r cross f, the magnitude of r cross f. This being f, this being r. I go to equation number 4, and I say, aha, that must be equal to the moment of inertia about point P, about the axis through perpendicular to the blackboard through point P, times alpha, which is the angular acceleration, and of course, this may change with time, and theta will change with time. However, there's one important thing. This torque is a restoring torque. It wants to drive it back to equilibrium. And therefore, we need a minus sign here for the very same reason than when we did the spring, that the force was minus kx and not plus kx. Now I say, aha, small angle approximation. By the way, alpha equals omega dot, first derivative of the angular velocity, therefore also equals theta double dot. I also wrote that there. And theta is this angle. This is the change of this angle that you see there, the second derivative. I say, aha, small angle approximation, then the sine of theta is theta. We've done that before, provided the angle is in radians. And so I'm going to get that mg b theta plus I relative to P times theta double dot equals 0. And now I already begin to feel it in my bloodstream. I already begin to smell the simple harmonic oscillation, and you too. Let's bring the theta double dot naked out here, plus mgb divided by I of P times theta equals 0. And this, for sure, is a simple harmonic oscillation in theta. And the solution must be that theta in time must be some maximum angle times the cosine of omega t plus phi. This omega has nothing to do with that omega. This is angular velocity, and this is angular frequency. This will never change. That's related to the period of oscillation. This is changing all the time. The theta dt is changing all the time. When the object is here, the theta dt has the largest value. When the object stands still, the theta dt is 0. So the angular velocity is changing with time, but this omega is a constant. And it is very awkward in physics that we use the same symbol in one problem and have totally different meaning. In any case, we know that this omega, the angular frequency, equals the square root of mgb divided by I of P. And so the period of an oscillation, which is 2 pi divided by omega, has to be this. This, by the way, is independent of the mass of the object. You may say, yeah, but there is a mass downstairs. Yeah, but there is also a mass upstairs, because the moment of inertia about point P has a mass in it. The moment of inertia about point P we find immediately by using the parallel axis theorem. If it were rotating about the center of mass, about this axis, then it would be a 1/12 ml squared, and so we have to add mb squared. We did something similar there. So this is 1/12 ml squared plus m times b squared, parallel axis theorem. And so now we find that the period is 2 pi times the square root of, I lose my m, so I get 1/12 L squared plus b squared, and I get here GB. And that is a very simple result when you come to think of it. I mean, this would have been a complete headache to do it in any other way. And this always baffles me so much. Some of you think that physics is difficult, but I always think of it the other way around. I always think of that physics is there to make very difficult things easy. Look at it. This is an incredibly complex system that is going to rotate about a pin, which is offset from the center, and here is a very straightforward prediction about the period. In our case, a B equals 40 centimeters, and it is an exact meter stick. So L equals 1.00, and B equals, it's about 40 centimeters, but we could be off by something like maybe 2 millimeters. It's not so easy to get that hole in precisely. So it's 40 centimeters plus or minus 0.2 centimeters. So that is an uncertainty of about 0.5%. I have upstairs L square and B square, and downstairs B, and that makes the error analysis a bit complicated. If I stick in the numbers, then I find a period which will be very close to 1.565 seconds. That's taking the exact numbers that I gave you for L, and I take for G 9.8, and I take the values for B. Since I prefer to be on the conservative side, I will allow for an uncertainty of about 0.01 seconds. And I would like to make a measurement and show you, what we get. So we have here the ruler. We're going to oscillate it. Small angle. Now we can be a little bit rougher, make it a little larger. Stop it first. And I will start it when it stops at my side. That is always the easiest to do. Now! 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Look, on the button. Way within the error. Amazing, isn't it? That such complex systems can be so easily dealt with in physics. It is 15, what is it, 0.71? And my reaction time is always 0.1 seconds, so the agreement is absolutely fantastic.